Hello, I'm Yasha from Barlan University. For our experiment, we need to construct and to design our experiment. The experimental design is the very important part of the whole experiment. The experimental design represents all the elements, conditions, and relations of the following consequences. The researcher must identify and control non-experimental factors. That means all the influence of the parameters, environment, that not our independent variables has to be controlled and eliminated. Select a sample of subjects. What exactly the researcher is going to research? What type of specimen out of many possibilities? Choose appropriate methods. The researcher must understand the whole available methods for this experiment and to choose most appropriate one, or many if needed. Then, researcher must select, construct, and validate instrument to measure outcomes. In experimental science, many instruments and technologies are used. The proper choice of those is a crucial part of the experiment. Then, a researcher must conduct a pilot study, something that has already been done by other groups, by other researchers, and to compare it, to validate that your measurement setup, the experimental design, is proper and get the expected results. And of course, you need to determine place, time, and duration of the experiment, so it won't take too much time to construct or conduct the measurement itself. In superconducting measurements, the most important part of the experiment setup is the cryogenic setup. So what is cryogenics? Cryogenics is the branch of physics dealing with the production and behavior of materials at very low temperatures. So cryogenics, it is science by itself. It helps other branches of science to conduct low temperature researches. Our requirements for the cryogenic system: we need adjustable temperatures from 4.2 to 45 Kelvin. This area is dictated by the critical temperature of magnesium diborate of 39 Kelvin. So we have to go a little bit above it. So we choose 45 Kelvin for that purpose. And 4.2 is the temperature for liquid helium. Below that, it's very hard to achieve. A temperature below 4.2 is very hard to achieve. Homogeneity of the temperature of the whole measured specimen. Because superconductor is very dependent, its properties are very dependent on temperature, we need to assure that the whole specimen we measure has homogeneous temperature. Versatility on specimen sizes. We might measure different sizes of superconductors, so we have to prepare it, the whole setup for different sizes and geometries. Thermal stability during the measurements. We're dealing with energy loss. Energy loss hits the superconductors, so we must assure that the temperature does not drift, does not change during the experiment. And of course, thermal insulation from the environment. We are dealing with very low temperature, so the heat from outside cannot enter our measurement system. In the specific experiment, magnetically and electrically neutral setup is a must, because during the change of currents and magnetic fields, some interaction might occur with the measurement setup itself, which has to be eliminated. And of course, you might keep your budget in mind, because too expensive system not always possible, so you have to choose appropriate price for the setup. So how can we reach the low temperature? The most common technique is to immerse the specimen in liquid gas. There are most popular gases. The first one is a liquid nitrogen. It liquefies at 77 Kelvin. It's very common, very cheap, pretty easy to handle, but the temperature is too high for our purpose. Some other superconductors can be measured in this temperature, but not in this case. Liquid hydrogen, 20 Kelvin, suitable for some measurements, but very, very dangerous, and requires a very complex protection and handling system. Liquid neon, 27 Kelvin, temperature is not low enough, and is quite expensive as well. And liquid helium, very common one, 4.2 Kelvin, but very, very expensive, and the whole world is trying to avoid using liquid helium when it's not needed, because helium, the Earth loses its helium. So another option to cool the specimen to desired temperature is to use a closed cycle cryocooler. This is the basic, the one we used in our experiment. It's the semi-atomic cryocooler. It can reach 4.2 Kelvin on the second stage and 45 on the first. It's a closed cycle. There is no liquid gases involved. It works on electricity. It has a high initial cost, but a very low operational cost. For this experiment, when we're about to measure a lot of measurements, different samples, this is the best options, especially when you're not sure what you're about to discover, and the measurement might take a very long time. This option is the most appropriate one. But it has a limited cooling power, and more advanced cryostat design is required. The other drawback is the vibration. It is some kind of motor that introduces some vibration if the measurement is very sensitive to it. This option cannot be used. So let's understand how the heat is transferred. There are three main mechanisms of heat transfer: the conduction in solids, convection in fluids or gases, and radiation through anything that allows radiation to pass. Thermoconduction is the transfer of energy between objects that are in physical contact. If something hot touches something cold, the heat transfers from hot to cold. It's proportional to cross-section, length, and of course the property of materials. The convection heat transfer is the transfer of heat from one point to another by the movement of molecules. This is what happens when you light a candle and the hot air molecules going up and the cold ones going down. This is what happens in a kettle when you boil water to make a tea. And thermal radiation. The all energy on planet Earth comes from sun by thermal radiation. It passes through vacuum air or anything that allows a light to be transmitted in it. So in our cryogenic design, we need to eliminate those mechanisms as much as possible to be able to use a cryocooler which has a very limited cooling power to reach the desired temperatures. Additional heat comes from joule heating in current leads. because we need to drive some current in our superconducting wire, the current must be connected to the power source, which is outside the measurement, the cold area of the setup. So some heat is generated due to resistivity of the cables and wires until it reaches the superconductive area. And this is additional load on our cryocooler. So the optimization of the current leads is a crucial part in the superconductivity measurements, because if we enlarge the current leads, it reduces the resistivity and reduces the general heating, but it increases the conduction from hot temperature to the cold area. So a proper optimization for the specific experiment is needed. When we use a cryocooler, the total heat power from all the sources must be lower than our cooling power at this temperature. For example, the cryocooler we used, if the total heat power is 4 watts, the lowest temperature will be only 7 K. And it has only 1 watt at 4.2 K. So if we want to cover the whole temperature spectrum, we need to reduce our heat income to 1 watt or so. So proper thermal design of the experiment is a very important and delicate task. So the cryostat. This is the actual design of cryostat we used in this experiment. It's all made of plastic materials, so they are not electrically conductive and non-magnetic, of course. But it has to maintain a high vacuum to reduce the convection heat transfer. So it was a challenging task because, for example, on the top cover of the cryostat, the pressure was about 2.5 tons. So the material has to be strong enough to withstand these forces and all the vibration involved, and the design must involve all the connectors, vacuum inlets, cabling, peripheral measurements, and so on, to build from the start. This is the actual picture of the cryostat. So we have actually 3 cryocoolers. The first one is for 70 Kelvin, 40 Kelvin, and 5 Kelvin. That's the lowest temperature we could reach in our case. These shiny things, these are radiation shield, because radiation heat transfer, it's actually a light. So we use a multi-layer mirror to reflect the heat comes from outside. And of course we have our current leads. The first stage is to cool it to 70K, then 40K, and just after that it goes to superconducting specimen. This is done to absorb the heat that comes from outside on the first 2 stages and to reduce the heat transfer to the specimen itself. This is our specimen here. It's a short, pretty much short length wire. Of course, we have to suck the all gases from it to eliminate the heat transfer by convection. So the whole system must be in a high vacuum. So we use a pump, the gauge, vacuum measurements, and of course thermometers. We need to understand the whole temperature distribution in the whole systems. This is how we can debug our mistakes and to make a better design to optimize it and to understand where the heat comes from. So we use many of them in different points. And we have a controlled heater because cryocooler it's non-controllable type of cooling. So if we don't have a heat income, it will reach its lowest temperature, and if we want to change it, we need to heat it to raise the temperature to desired value. So the highlights for the cryogenic system design. We need to maintain a high vacuum in the system to eliminate convection heat transfer. Current links and cabling optimization to reduce joule heating and heat conduction from outside environment. Radiation shields to reduce thermal radiation from hot parts of the system. In our case of measuring energy loss in a superconductor, this energy loss is transferred to heat, and we need some extra cooling power to absorb this heat. Of course, precise temperature measurements in many points, controlled heater to achieve various temperature, and mechanical stability. The next talk will be about the experimentals and the research methods of these experiments. Thank you.